Okay, so this is going to be the third lecture. I've kind of learned to divide and conquer after a snafu with the recording issue. So that's why I'm breaking this up into a different section on just kind of the stoichiometry on it. So I'm going to kind of go through and explain how you can use pressures and to do some stoic and review some stuff as well. So let's say that we've got this reaction where you have 2 BrCl, which can reach a point of equilibrium where you're forming bromine gas and chlorine gas. Okay? So let's say that you've got 0.1 moles of pure BrCl, and that's contained in a 2-liter container, and you're at 298 Kelvin, and we want to find the initial pressure at the beginning. Okay, so you've got your number of moles, put that in there, you know R, you've got your temperature, you have the volume of 2 liters. You plug all that in, you have a pressure of 1.22 atmospheres. So within this container, okay, here's this 2-liter container, that the pressure at the beginning is going to be 1.22 atmospheres. Now, what's important is that that is pure BrCl, okay? That's it. The reaction hasn't started to decompose yet. So that within this system, there's no bromine and there's no chlorine, okay? So that's going to be important later on. Now, if you're asked to write the equilibrium expression, when you have gases, you can actually write it one of two ways. You can either write it in terms of concentrations, which would be molarity, which would be moles per liter, or you can write it in terms of pressures. Now, obviously, if you in this situation, you can pick either one. So this is actually a question off of an old AP exam. So if they just tell you to write the equilibrium expression, you could either put it in terms of concentrations or you can put it in terms of pressure. But you want to be careful that they're not indicating, oh, we specifically want an equilibrium in terms of pressure or in terms of concentration. So if they just tell you to write the equilibrium expression, remember it's always products over reactants, old school, not a big deal. Now, we're going to let this reaction go for a while. And after a while, you're told that 42% of the original BrCl has decomposed. Now you actually want to calculate the value of K. So remember, K is what's happening at equilibrium. Okay, remember that's the only time you use K is what's going to happen at equilibrium. Now, so this is just a rice chart. So initially we started at 1.22 atmospheres, where there was no Br2Cl and there was no chlorine, okay? So this was the initial setup. So we're just using a rice chart just like we've done before. Now, because of this 2, we're going to lose 2x here, but then we're going to add x and we're going to add x over here. So that the reason that this 2 is existing is because of the fact that there's 2 BrCl. So that we're going to lose twice as much here on the BrCl side, then we're going to gain that over here on this side. Now, this 0.71, how I got that is that you were told in the problem that 42% of this stuff has decomposed. So I took 0.42 times 1.22 and I got 0.51. So that means that 0.51 atmospheres, and that's the beauty of working with pressures. You can either work in atmospheres or you can work in moles. It's going to be the exact same relationship. So, since I know that 42% of this, which is the 0.51 atmospheres, if I take 1.22 and I subtract 0.51, that means at my equilibrium pressure, this is going to be 0.71. So now, if I take the 0.71, okay, which is what's going to be left over, now I can figure out what these x's are. So I know that that 0.51 that I'm losing has to equal, okay, x plus x, because whatever I lose here on that 2x is what I have to gain over here. So what that tells me then is x is going to be 0.26. So if I take the 0.26, right, now I know my BR2, I know my Cl2, and now I've got all the numbers. So now I can calculate my value of K. So all I did was just a simple substitution of substituting those numbers in. And if you do all of that substitution, then you get a value of, I think it's like 0.13. Okay? So here's what I just want you to see out of here, that if you're going to do stoich, you can either work with moles or you can work with pressure, depending upon the setup. Okay, now let's talk about this decomposition reaction. So I got calcium carbonate, it's a solid, and I'm going to decompose it into calcium oxide, which is also a solid, and carbon dioxide gas. So there's a whole bunch of different things that you can do with this. So let's say that you've got 152 grams of calcium carbonate, and you're told at standard temperature and pressure, remember at standard temperature and pressure and gas laws, that 0 degrees Kelvin and 1 atmosphere of pressure. So I'm going to calculate the volume of carbon dioxide I'm going to produce. Now, this might be one of those random things you might need to know. Remember, carbon dioxide as a gas acts as like a fire extinguisher. So if you actually did this, if you wanted to verify that you were producing carbon dioxide, if you took like a burning wood splint and put that into the test tube as you're heating this stuff up, it would go out. Now, if you were producing oxygen and you put the burning wood splint in there, it would glow much brighter. If you think you might be producing hydrogen gas, remember when you put hydrogen, if you have hydrogen gas and you put a burning wood splint in, you get that popping sound. So this is just kind of general guidance information that you if they happen to throw it out on the test. Carbon dioxide puts flames out. Hydrogen makes the test tube pop. Oxygen makes the test tube glow much brighter because of the fact that there's oxygen in there. Okay, so the whole key to this is that you're told that it's at standard temperature and pressure. At standard temperature and pressure, 1 mole of any gas is 22.4 liters. You do the math, boom, you get 34.0 liters. Now, the other thing that you could do with this, if you were given this, and again, this is where you can tie a bunch of things together. Let's say that you want to predict the sign of delta H and delta S. Okay, well, let's go up here. So we've got 1 mole of solid. We end up with 1 mole of solid on this side, but more importantly, we end up with 1 mole of gas. So right away, I'm going to figure that my delta S is going to be a positive number. So right away, oh, Mother Nature likes this, okay? Mother Nature is digging this because I got a positive delta S. Now, because of the fact that I'm breaking bonds, I'm dumping energy into the system, guess what? I'm also going to have a positive delta H. Now, hopefully this makes sense, because you can look at this and go, oh, okay, hey, I got a positive and a positive. That means it's dependent upon high temperatures. Now, logically, I couldn't end up with a negative delta H, because if I had a negative delta H with a positive delta S, this reaction would be spontaneous, and we could never have calcium carbonate. Calcium carbonate is kind of important. Calcium carbonate is limestone. So if calcium carbonate spontaneously decomposed into calcium oxide and carbon dioxide, we could never have limestone to use as a building product, because it would always decompose into calcium oxide and carbon dioxide. Okay, so let's say that you have a combustion of methane gas in the presence of oxygen, and you always get carbon dioxide, and in this case, I'm going to tell you that we're going to get liquid water out of this thing. So let's say that you have methane. Well, this combines a whole bunch of different things. So let's say you have methane, and you have 2.8 liters at 25 degrees Celsius and a pressure of 1.65 atmospheres. So if you find the number of moles using PV equals nRT, and I did this just to save some time, you get 0.189 moles. Here's the conditions for the oxygen: 35 liters, 31 degrees Celsius, 1.25 atmospheres. If you do the math here, you get 1.75 moles. Okay? All that was just solving for N from this. Now, here's what's going to be more important. You have to recognize this as a limiting reactant problem. You have 0.189 moles of methane and you have 1.75 moles of oxygen. So you have to figure out, okay, hey, which of these is going to run out first? So here's the simplest way that you can do this one. There's various ways. Here's one option. Is that if you start with the 0.189 moles of CH4, and if you want to figure out how many moles of oxygen that you have to react with it, all it is a simple stoichiometric relationship, and I got 0.378 moles. So what this means is that for the methane to completely react, that's only going to need 0.378 moles. I have 1.75 moles available. So that means my oxygen is going to be in excess because I have a lot more moles of oxygen than I do that is going to be needed to completely react with the oxygen. Now, if you wanted to get clever, if you wanted to figure out how many moles of oxygen are left over, you just take 1.75 minus that 0.378, and that would tell you how many moles of excess oxygen that you had that would still be unreacted in the container. Okay, so if I want to figure out the moles of carbon dioxide, all this is I went up to my stoich and I said, hey, I got 0.18 moles, 0.189 moles of CH4. It's a 1-to-1 ratio. I got 0.189 moles of carbon dioxide. So now if I want to calculate the new pressure, and let's say that is 2.5 atmospheres and 125 degrees Celsius, that's after the combustion, which makes sense because, oh wow, it's an exothermic reaction, so the temperature went up. So now if I want to find the volume of carbon dioxide that was released, I got 0.189 moles of my carbon dioxide. I know R, I know the new temperature, the pressure is 2.5 atmospheres. I'm going to do 2.47 liters of carbon dioxide gas. So anyway, kids, so that's just how you can use this to do some stoich. That's going to, like I said, that's going to be more on your assignment, but I just wanted you to kind of show you some tricks that you can do with stoich and gas laws. So this is the last of the gas laws.